Kia ora koutou. This is question 3a from last year's scholarship calculus exam. I think this is probably the easiest question in the paper, or one of them, especially because they give you a hint about one way to do it. And if you've done log differentiation, you will recognise the hint as just telling you to use log differentiation here. So we're given a function and we have to differentiate it and find the exact value of the first derivative when x equals 0. Okay, and so here's the hint. So I'm going to do this question twice. I'm going to do it once using log differentiation and once not using log differentiation. Now, doing it not using log differentiation was actually not as bad as I expected, but you have to do a few simplification steps first in order to avoid a big mess. So if you don't know log differentiation, it's pretty easy to learn. First of all, you need to understand implicit differentiation, so you can go and find some of the videos I've done on that. And they're on, I think they're now on the Scholarship Building Blocks playlist as well. If they're not, if you just search up implicit and maybe look for the 13 MCA playlist, or email me if you can't find them. There are heaps of videos that use implicit differentiation, but there are also 3 where I just teach the method from very easy examples, building up to harder ones. And then on the Scholarship Building Blocks playlist, there's a video on log differentiation, which is an application of implicit. That one should be pretty easy to find. So when we've got a function that is a bit of a mess, especially if it's got e to the power of stuff in it, we can see that if we can take logs of both sides, things will get much easier. And that's what log differentiation is all about. So we start off by taking the natural log of both sides. We're going to get the natural log of y is equal to this. So I'm writing this out really slowly. It would be fine to go straight through to the log split up if you were doing your working, if you're confident. So we get the natural log of y is going to be equal to the natural log of e to the 5x plus the natural log of root x plus 1 minus the natural log of e to, why is it doing that? Just a sec. Okay. I think I fixed that up. So this should be the natural log of e to the root x plus 1. We're going to apply a whole lot of stuff from level 2. We're going to bring down the powers and recognise that the natural log of e is just 1. So we have 5x plus 1/2 log of x plus 1 minus root x plus 1. And I'll write that in fractional power form. Okay, so I'm bringing down this power here, and then the natural log of e is 1. Right, now I'm going to differentiate, and the way that I do that is I'm differentiating with respect to x. So that means that on the left-hand side, I have to use implicit differentiation. I can't differentiate directly with respect to x, but I can differentiate with respect to y, and then use the chain rule. Right, so this is how implicit differentiation works. Left-hand side, we get that, and on the right-hand side, we have a really easy derivative now. We have 5 plus 1 over 2 times x plus 1. The derivative of the inside function is just 1, so we don't even have to do the chain rule properly. We do the chain rule, but we don't get anything messy. And now here we've got 1 over 2 x plus 1 to the power of 1/2. Okay, the last thing I've got to do is to get an expression for dy by dx, and dy by dx is f dash of x. So in this step, we're going to have y, which we'll just put like that. So y into 5 plus 1 over this minus 1 over 2 root x plus 1. And we need to evaluate this at 0. So when x is equal to 0, y, going back to the start, we're just going to substitute 0 in here. So y is equal to e to the 0 times the square root of 0 plus 1 over e to the square root of 0 plus 1. That works out to be 1 times 1 over e, which is just 1 over e. Okay, so we've got that, and now we're going to substitute that into here. So f dash at 0 will equal 1 over e into 5 plus 1/2 times 0 plus 1 minus 1 over 2 root 0 plus 1. And that means that we end up with 5 over e for my final answer, okay, which I think you'll agree really didn't involve too much thinking if we're confident with log differentiation. So I decided I'd have a go at doing this question without doing log differentiation. Usually it's horrible, but here it's actually not that bad. However, I think you're much more likely to make an algebraic error. So when you first look at it, when I first looked at this, I saw the hint and I decided straight away that I would get on with log differentiation. And I would have done that even without the hint. And I thought, oh yeah, it's going to be quotient rule. It's actually not quotient rule. It's easier than that. It's just the product rule because you've got a common base here. So the first step we can do here is a simple rewrite where we get e to the 5x minus root x plus 1 times x plus 1 to the half. So if we just get on with it, we're going to do the product rule. And we'll get dy by dx. And so it's the first function, so u times the derivative of v. It's going to be times 1/2 x plus 1 to the negative 1/2. And now we switch it over. Plus, I'll just shrink my screen a wee bit. Right, what have I got here? Well, it's plus this function, which is root x plus 1 times the derivative of this one. So by the chain rule, I'm going to have 5 minus 1/2 x plus 1 to the negative 1/2 times e to the 5x minus root x plus 1. Now, that wasn't too bad, and the reason that I'm kind of feeling okay about that is all I have to do at this point in the question is to shove in x equals 0. It's not like I have to do a whole lot more with this or lots and lots of rearranging. So when x equals 0, what do we get? Well, we carefully are going to put things in. So we're going to get e to the power of 0 minus the square root of 1 times 1/2 times 1 over the square root of 0 plus 1 plus the square root of 0 plus 1, 5 minus 1 over 2 root 0 plus 1. And up here we've got e to the same power as before. So that simplifies really well, right? I get e to the negative 1 times 1/2, because this is just 1, plus, well, that's just 1 times all of this. So here we've got 5 minus 1/2 times 1 over e. Getting a common denominator, well, let's go a bit slower. 1 over 2e plus 9 over 2 times 1 over e, which equals 10 over 2e, which gives you 5 over e, which is the correct answer. So I'm kind of curious about whether any of you watching did do it that way and prefer that way to log differentiation. If I can use log differentiation, I almost always will use it. It's one of my favourite techniques that we do in scholarship calculus. It's partly because it reduces the chances of error and it makes the derivatives just so much simpler to work with. But it's fine if you did it the long way. You would definitely get 4 marks doing it that way. I'm just curious about whether you got there without either mucking up your substitution or your algebra. Thanks for watching. I'll do some more questions later on today.